variable is time, as measured in seconds or minutes, then we would call that motion. And here you see just organism moving in the torso. If it's time measured in age, and we're looking across the population, then looking for trends in that kind of data falls more into the realm of shape regression. And these are the two main applications of the work that I'm going to present today. So for the next few slides, I'm going to refer to 4D imaging. And this really does just refer to an image where the domain is four-dimensional. So at every time point, in a 4D image, we can produce a full three-dimensional volume image representing internal anatomy. And the question is then how to estimate these from real data. Now, motion is really important for various applications. In radiation oncology, it's really important to get good information about the motion and not just avoid it. They want to use the motion estimates that we get to inform the treatment planning phase. And the standard way to do this is to oversample the data when they're taking a CT scan, for instance, then retrospectively bend the data to produce a series of 3D volumes that they register using standard registration techniques to get some idea of the motion. But the problem is that these bending processes suffer from a lot of motion artifacts due to various causes. As you can see here at the top of the liver, we're seeing some of these motion artifacts. You get this ghosting and repeats of certain surfaces. And if you try to match two of these images to one another, you'll get really unrealistic motion estimates. And so we want to have a nice estimate of the motion, so our approach is to skip this bending process, which is causing problems. So the first step towards our model is to model the actual data acquisition and the scanner geometry. So most imaging modalities, including CT, MRI, and PET, can be described as the patient goes into the scan and you collect a series of parcels of data, and I'll call these DI. And these could be individual 2D projections if you're getting a cone beam scan at different angles around the body. They could be 1D for fan beam. They could be lines of K-space for MRI, and so on. But in general, we'll use this abstract notation with the PI, indicating just an abstract linear operator. And by modeling this in the abstract like this, we can kind of think of this as plugging in different modalities. But we'll develop the whole theory in the abstract and develop our methods with just PI. The next step in modeling the data acquisition is to actually model the noise in the data. And this is really well studied for most imaging modalities. For low SNR photon counting, like in PET or really low SNR CT, then the noise follows a Poisson distribution, which has this as its log likelihood. For higher SNRs and for K-space MRI data, the noise is actually Gaussian, and its log likelihood has a familiar form of a sum of squares. So maximizing this log likelihood, since it's a negative sum of squares, corresponds in some sense to a least squares kind of estimation. For our purposes, we're going to model the motion of the actual organs during the scan. And what we use is a commonly used model in image registration now called LDDMM, where we model the flow, the time change of a deformation via flow along these velocity fields. So for every point in the anatomy, x, at time 0, it's at x, and at future times, that point's position will be modeled as h of t of x. And the time change of h will be modeled as the velocity at that point at time t. And so the parameters of this deformation are actually a set of velocity fields at every time. They're densely defined in space and time. And the flow along those velocities determines the deformation. Now what's nice about this model is that if the velocity fields are all smooth, meaning some level of differentiability, then we're guaranteed that the deformation is what's called a diffeomorphism, meaning that it itself is differentiable and it's one-to-one onto invertible. And this implies that if you have substructures embedded into the torso, for instance, then we won't estimate that they rip apart or overlap or that new particles appear and stuff like that. So we get somewhat feasible deformations using this model. And we'll enforce this with this regularization term, which is takes the form of just a squared Sobolev norm. And this is a commonly used kernel in the literature. What this flow allows us to do in particular, and this is one of our contributions, was to enforce incompressible deformations. Because if all of the velocity fields have zero divergence, then we're guaranteed to have a unit Jacobian, which means that the local volume change, the local volume will not change at any point in that area. And so one of our contributions was to find an efficient way to enforce this as a hard constraint, so that when we're modeling incompressible organs, we can make sure to model a feasible deformation. Yeah.
Which organs are incompressible?
Most fluid-filled organs, like the liver, is going to be one of our big examples. Modeling the lung as incompressible, for instance, would be probably a bad idea, but the liver is one major example. So combining our data likelihood, which is, as I said, the sum of squares, with our regularization term, we get a posterior probability. And maximizing this gives us our full maximum a posteriori algorithm. And so we'll minimize this, or maximize this for both the base image, which is a 3D volume, I0, and a set of velocity fields. And you notice that this setup has all the things I just mentioned. It has the sum of squares data term. It has the motion model, modeling the deformation as a flow along these velocity fields. We're regularizing those velocity fields. And we can plug in different image modalities by just changing PI. So to repeat, we're just going to optimize this in an alternating fashion. So we're going to do a gradient descent where we alternate between stepping in the gradient and I0, and then we'll update the velocity fields. And we'll update these jointly until they both converge. So we performed a simulated cone beam phantom study. So this was actually a 3D volume phantom, and we simulated a cone beam scan. Here you see the phantom, and here you see the CT reconstruction when the phantom is moving during the scan. And as I said, since we're doing this alternating algorithm where we jointly are optimizing I0 and V, as our image estimate improves, so does our velocity field estimate, and vice versa. So what you're seeing here is each frame of this movie, if I get to play that, is a iteration of our algorithm. So it starts out looking very much like the static reconstruction, but as our velocity and deformation estimate improves, that allows us to improve the base image and so on. And you see that eventually we estimate something very close to the true phantom. But of course our output is the base image as well as velocity fields. And so here I'm playing just a single slice through the resulting 4D image. And we've estimated this translation motion for this case. We've also done some real phantom studies. Here I'm showing a lung phantom from the Huntsman Cancer Institute. This phantom has a piston, and at the end is a spherical tumor. This phantom also has a simulated chest wall with a marker block, just like a real patient would have, which allows us to correlate the motion and the internal anatomy with the external surrogate. And we ran a couple of scans with this phantom. On the left, you see a typical X-ray tube currents scan, and then the top is the current state-of-the-art binning approach. So this is the images that are actually produced on the scanner. And at the bottom is an alternative method of binning called amplitude binning. But you see that they both have problems. They both show image artifacts. On the right, we see a lower SNR. Now we turn down the X-ray tube current to 10%, which is kind of not a real practical number to run on real patients. But it's this data that we'll use in our algorithm.
So Jacob, why are the big chunks missing?
So in amplitude binning, since the patient's breathing traces can be irregular, you might not have data at every amplitude and every slice. So in it, in order to keep from comparing just the same slice over and over again for many different amplitudes, I'm showing it as black lines. But you could throw in the same slice that would correspond to a much different amplitude. So we use the data on the right and fed it into our algorithm. And we're able to play back the motion correlated to the breathing signal. And you'll notice that we don't see any of those these jaggy motion artifacts in our resulting image. And you also might notice, if the projector is working right, that the image quality in terms of SNR is much improved. Since we're using all the available data, we're able to really increase the SNR of our output. And this has a real impact for CT, which is an invasive imaging modality, because like I said, we're using the low SNR data right here, but we're getting an SNR in our output that rivals that of the high SNR in our data. So what this could allow is a really significant reduction in dose to the patient during a scan.
Jacob, that was a very irregular signal you were running right there. Where did that come from?
So this is a real patient. That phantom is actually programmable to model whatever breathing signal you plug in. And so this was just sort of a typical patient. It's not the best patient, but we wanted to test that. We didn't want to just give it a sinusoid, so we wanted to kind of challenge it somewhat. And you notice that there's drift, and you see these kind of breathing signals quite a bit. Not every patient breathes just perfectly regular and repeating. So this is one of the big challenges to our algorithm as well. So we've also done another phantom study with Huntsman. Martin Zegedy at the hospital has actually developed this phantom, which is very similar to the last phantom, but instead of using a rigid tumor surrogate, we're going to, or fake tumor, we're going to use an actual excised pig liver. And this is placed into a KH solution bath. And the piston drives a nonlinear deformation in the liver now. And Martin has shown that this reproduces motion that's very similar to what's seen in a real patient. Now, what's convenient for us about this is that we're able to implant whatever markers we want into this excised liver, and we can use those for tracking in a real validation study for us. So what I'm showing here is we implanted an RF tracking device, ran the phantom, and tracked the motion. The result of that is the blue dots. So that's what we're going to use as our ground truth. We kept it running and ran it through a CT scan, and then manually on a 20-phase bend data set, manually demarcated the position of that tracker. And so you see that the circles match really well to the blue dots. But then we ran that data into our algorithm, and the output is this solid line, which you can see, even though the circles match up to the blue dots, our algorithm sort of splits the difference between these two sides of this loop. And the reason that this track looks like this is one of these sides corresponds to inhale, and the other corresponds to exhale. And this is a hysteresis loop. So as the liver's moving, and this is seen in real data, points in the anatomy take different trajectories based on whether you're inhaling or exhaling. And in this case, it's resulting in a loss of accuracy. Since we're splitting the difference here, we're off by up to like 3 or 4 millimeters.
So this was with your setup? It had hysteresis?
It had hysteresis, yeah. That was one of the
nice.
Yeah, that was one of the really nice surprises out of the from looking at that raw data.
So that was a surprise?
Well, I was surprised by it. I don't know, maybe Bill thought it would happen.
We might have hoped.
Yeah, but it's really nice that when you look at in the literature at real patient studies on hysteresis, that they look just like this, like a beautiful hysteresis loop. Width is similar and everything. So, like I said, we're kind of splitting the difference here. So we modified our algorithm to try to get a better match to the ground truth. And what we did was just said, okay, let's place the base point. Let's estimate a base image at end exhale, so at one end of this loop, so up here. Then let's estimate a different deformation, split the data based on whether you're inhaling or exhaling, and estimate a different deformation for each side of the loop. And the result is this dashed line. So you see now that we're really nailing the deformation for most of the whole loop. And the only problem with this that we've seen so far is that the opposite end doesn't exactly close back up. So we're off by about 1.5 millimeters to 2 millimeters here at the far end. But we were able to improve our estimate quite a bit. So besides the validation studies, we've also looked at how this performs on real patient data in a retrospective study. Here I'm showing a bin data set for a real patient, and you notice that there's motion artifacts, and that the motion artifacts that sometimes go away. This is 3 different phases of breathing. And if you tried to match these images together, you get really non-realistic deformations. When we plug this into our algorithm, the first thing you might notice is the jump in SNR, which I've already discussed. But you also notice that although those motion artifacts haven't totally gone away, they've been reduced by this averaging, and that they also are consistent across the breathing cycle. So now we don't have to match non-matching images. We actually have a more realistic model. And we use this data to kind of validate our incompressibility constraint. So as I said before, we have the option to enforce a hard constraint that the deformation is incompressible or not. And if we don't enforce that, we see that we get the same sort of image. This is a deformed image with incompressible deformation versus compressible. So as far as the image is concerned, there's not really much change in enforcing this constraint. But on the bottom, I'm showing the log Jacobian determinant, which is an indicator of local expression or expansion or compression of the individual volume element. And you see that without our constraint, we are actually estimating expansion of the top of the liver and compression of the bottom of the liver in certain cases. And since, as I was saying to Ronnie earlier, the liver is a fluid-filled organ, we know that this is not a realistic deformation. Whereas when we enforce incompressibility, we see that we actually do preserve volume. So this has more of a chance of being realistic. So this isn't really a validation study, it's more of an invalidation study of doing compressible deformations on incompressible organs.
Do you have to enforce that it's incompressible on the whole image, or just can you do it just in the liver? Say the liver and the lungs in the same capture.
That's a great question. That's one of the reviewers on the journal version of this brought that up. In our current version, we do have to enforce it over the whole domain because we do it in Fourier domain. But recently we've implemented a version where we would mask we do like a thresholding on the actual base image and then propagate that forward to give it, we smooth it a bit so that we're ensured smooth deformations. So you move this mask forward and then use that as a ratio to combine the incompressible and compressible velocity fields. And so doing this, we're able to produce a deformation that looks like completely flat in the liver, but then, for instance, this area remains lit up. So the lung is able to compress, but none of the bright spots compress. So
you don't have the result of that?
So I didn't get the figure in for the talk because it was just yesterday afternoon that we got it, but
you showed it to me yesterday.
Yeah.
Well, that's better.
Sorry about that.
We had all night.
Yeah.
So you've taken all of the amount of change in volume out of this. Is this really realistic? Are you enforcing this too much?
Yeah. So for the liver, for instance, which is the main organ, for instance, if we're looking at a liver tumor, it's not that unrealistic. There are volume changes, but they're mainly due, as far as I'm aware, to perfusion and pulse and overall blood pressure and stuff like that. But they're not due to the actual just motion of the organ as a whole. So as far as an individual organ is concerned, yeah, I think it is pretty valid. But as you said before, doing it on the whole domain, there's going to be certain parts that do compress, like the lung is probably the main one, air-filled organs. So that's what led us to do this kind of masked approach, which is sort of an engineering approach, but it would be probably more useful in practice.
And where if you're over constraining, you're forcing it too strictly.
Yeah.
It's possible. These two, the deformation and the original image, sit over top of each other, I see.
Yeah.
We have them arranged. So why is it that very bright, intense red region at the top of the deformation image. I mean, how does that seems to overlay a void region almost in the image.
So, yeah, so this, during the deformation, this, for instance, could be all coming together. Like these corners would be pushed up into here as the liver is pushed farther towards the top of the image. It has to compress to shrink away from the liver.
Right.
And so that's really what you're seeing is that this front here is moving, and it doesn't have room on the top to fully dissipate like it does on the bottom. Because we have this smoothness, so the front will move and then it'll be smoothed by the
So wherever you have a compression, you should have a decompression somewhere nearby.
Yeah, and I think that's what's happening is
Yeah,
it's like two sides of the same coin here, but at the top you don't have enough room for it to flatten.
So your boundary conditions, are they zero?
So the boundary conditions on the whole are, but we also pad it with empty space. So we'll.
So I mean, objects moving out have to really actually compress at the edges, or they actually move out?
So they're able to actually move out. So I'm showing the clipped. We don't compare outside of our of the original data.
Move out the padded area.
They can move out into the padded area just and come back in, so that we don't lose track of them. But they don't. We don't enforce anything about it. Okay, so as I said, this was real patient data, and here I'm just going to show a video of a bin data set. And this is showing all the things that I've discussed before. We've got motion artifacts and a pretty grainy image. And this is actually like kind of the state-of-the-art binning procedure for 4D CT scan. And here is the actual 4D image produced that I was analyzing in the last data set, or last slide. And you see we get a much smoother model of the motion. We don't have to go back and do registration. We already have the model. We also have this big jump in SNR, as you can tell. It's much less grainy. And whatever image artifacts remain are at least consistently preserved by the motion. So we don't have an unrealistic deformation being influenced by those motion artifacts. And I'd make the point again that this SNR increase is really important in this application. This is a much cleaner image, but most clinicians would probably prefer to have reduced dose to a much cleaner image. So like in my first Phantom study, we turned down the dial to 10%, but we could even possibly go lower and retain the same image quality in terms of SNR because we're averaging all the data and we're not throwing it away in the binning process. So that could have a real clinical impact.
So what is the application here? What are the images used for?
So they would be used to tumor motion envelope, for instance, would be drawn on right on the liver, and then that 3D structure used to plan a dose delivery in a real radiation treatment.
And so it's assumed they'll breathe the same way when they're treated? Are they treated right away or days later?
They're treated days later, but the chest marker is. Yeah, so there's a lot of elements to this. They have a chest marker that we assume is correlated to internal motion, and we also assume that on the next day that correlation would still hold. But there's a certain amount of alignment that needs to happen when they come back for the next day, and these things are kind of currently taken care of with a second scan right before their treatment, without removing them from the couch, for instance.
So I think you're hitting on an important point that you should emphasize related to this question of, do we assume they breathe the same way? You pointed out there are some assumptions that there is this correlation between the external surrogate and the internal markers.
Right.
But you also just pointed out that we get a new scan immediately prior to each of these treatment corrections.
Right, and so in the current kind of paradigm, we would do the simulation scan and then do all of our motion modeling, and then come back and use that same motion model on the treatment day. But my laptop's going crazy. But you could also imagine, since we're getting a new scan anyway, building that model for that specific day and adapting our treatment likewise. But all this kind of depends on having a good, reliable model for the motion. My laptop just turned off. Okay, so sorry about that. yeah, so there's a number of assumptions that go into it, and not least is that we're assuming that there's that correlation between the marker and the internal anatomy. And the hysteresis results that I showed kind of fly in the face of that assumption, because for any one specific chest wall height, whether they're inhaling or exhaling, it's going to determine where particles actually are. So we're looking for more realistic models for it.
So while we're waiting for your laptop to come back on, why don't you characterize your understanding of what current state of the art is, because what you're looking at is some new stuff here. What do we do in the clinic today with regard to motion and
so right. So currently, a sim scan is done on the simulation day, and this is binned into say 10 or 20 different phase volume images, and then those volumes can be played back like a movie, like what I showed, and that'll be shown in like a 3-pane view, and the clinician will actually contour the tumor. This could be the physician or someone familiar with the tumor location. They'll contour on the imaging where they think the tumor is moving. So they'll contour the entire motion envelope. And then that motion envelope they add a little bit of a fudge factor, a margin to it. And then that's run through the inverse problem optimizer that optimizes the actual beam angles and so on. And then there's a certain amount of manual part to that too. And then that is what's used on the day of treatment. And the patient's placed on a couch when they come back in on the treatment day, taken a scan, and then that 4D scan is aligned to the sim day's 4D scan. And this is all kind of done kind of in a semi-automatic way. So the couch is able to move in 6 degrees of freedom, and that shift is done in the treatment room as well. And then they just use the plan that was planned off of the simulation scan. So one thing that we could do with this kind of technology is to just, instead of having to segment the motion envelope manually, pause the video, segment the tumor on a single frame, and then propagate it out to get an automatic motion envelope. And then we could also do like higher order things, like for instance, we could start thinking about what fraction of the time is spent in each phase of motion, and try to, I mean, this is a long way off, but try to update our treatment accordingly to have the most reliable scan. And then really far off would be to be able to model the motion reliably during the scan and react in real time. But that's quite a ways off. Nice. Yeah, sorry about that. It just power spike or
I
something.
mean, the 4D treatment planning and gated delivery is not that far off. I mean, gated delivery is routinely done.
Gated delivery, but yeah, but what I meant by that was actually tracking and keeping track of what dose you've actually deposited, and building a real model of the treatment process in real time, and then updating the shape of the beam and the locations.
So lastly, you talked about the significant improvement in signal-to-noise ratio, or do you have a feel? Today we do image guidance where we take images to decide if we're going to hit the target today. Do you have a feeling that we're completely unconstrained in our ability to do all the imaging we want, or are we somewhat limited because of dose concerns?
So no, that's one from the impression I've gotten from talking to clinicians is that there is some concern that the amount of diagnostic imaging being done is actually depositing a significant level of dose in the patient, and it's almost worrisome how much is actually being done. An ordinary non-4D CT scan, for instance, deposits quite a bit of dose. We're talking about oversampling 16 to 20 times for a standard 4D CT scan. So it's basically like you go in and get 16 to 20 CT scans on the same day, and then you do that maybe 5 times over the course of your hypofractionated treatment. So if we could reduce that to 10%, I mean, that could be actually really exciting and could enable more imaging to be done, and actually at the same time be a little bit safer for the patient. So sorry for the interruption. I think it's going to work. Okay, so we've basically seen the CT results. But as I said, since we model this in the abstract, using these abstract PI operators, if you remember, we can basically just plug in a new modality. And that allows us to switch our whole application. And the other big application that we want to apply this to is cardiac MRI. And so we've started to do a few feasibility studies, and we want to develop this into a real study. But what you're seeing here is a 2D simulated MRI. It's a 2D phantom with some simulated motion and noise added. And this is a torso that's simulated to be breathing. And we see this blurring artifact when we just apply a standard IFFT static reconstruction. We can also retrospectively bend this data just like we would the CT data to try to get a bit better image quality. And we see that this is at least a little better than the previous slide, but still quite a bit of blurring of internal structures. With our 4D reconstruction, we're able to resolve these internal structures a lot better, which is the main application for MRI. You want to actually see where the substructures of the heart are moving. So this work has resulted in a few publications so far, a couple of conferences. We first presented this at ITME, and then at a computer vision conference, VisApp. And I'm resubmitting this to medical image analysis, the journal version, in the next couple weeks. So that's basically what we've done with motion to this point. And as I said before, there's basically two halves to this talk. This is the same plot I showed before. And as I mentioned, the other end of the plot of this curve does not match up on both sides on our hysteresis corrected reconstruction. And this kind of bothered me. And this kind of led me to look at other models of motion that would allow us to actually enforce that the deformation is periodic. So we ended up looking at a lot of different new models, commuting flows, shape spines, and some other avenues without a lot of success. But it did lead us to start thinking about the overall shape change model in kind of a new way, and thinking about different classes of curves on Riemannian manifolds. And in particular, it inspired kind of a new importance for us to place on parametric models as opposed to non-parametric models. And when I say non-parametric, I don't mean that there's no parameters, just that there's so many parameters to be treated as infinite. So we previously had to estimate every velocity at every time point. That's a lot to estimate, so you end up regularizing and so on. In a parametric model, you would just have sort of a lower number of parameters for your model, which could be compared between different data sets. So this figure is going to be really familiar to everybody in this room. We're given some real value data and just fit a line through it. Okay, so this is just classical curve fitting. And we end up reporting the R-squared value, which is some indicators between 0 to 1 of how good of a fit we've done. But you see that the black line wasn't as good of a fit as we'd like, so we fit a little bit more flexible model, quadratic polynomial. And when we fit the cubic polynomial, we see we've pretty much nailed the data, and we've got a really high R-squared. So what we're actually doing when we do this is least squares, and this is kind of one of the typical least squares applications. And I don't want to belabor this too much, but suffice to say that we have a polynomial, which is determined by its coefficients. These are the parameters. We plug that into a least squares objective function, and we minimize this by taking the gradient with respect to c, setting it equal to 0, and we can solve this closed form. And this is the typical least squares algorithm, the way it's generally implemented. Now, that's all fine and good, but now what if I have a data set that lies on the sphere instead of real value or vector space? Now, say we're given data on the sphere and we want to fit some class of curves to it. We don't have currently good methods for doing this for general classes of curves. And one of the reasons is how do we even define the familiar classes of curves that we're used to? How do we define a polynomial on the sphere, for instance? And so we're going to attack this problem. And we don't want to do something that's specific to the sphere. We want something that's a very general theory that will apply to a bunch of different interesting spaces. And these could be surfaces or other spaces. The general class that we're going to be considering is Riemannian manifolds. And I put the definition up here, but you don't need to read it. This is even kind of a loose definition. So just think for the time being of a surface like the sphere. And I'll explain whatever's missing as we go. But the main point is that by modeling this in this real nice abstract way, we can apply this to multiple different problems. So, as I said, we don't have a default definition of a polynomial yet. So this is the one thing that we had to come up with first. A polynomial, you might think of its algebraic definition. This is the most common form of polynomial, just a sum of powers of the independent variable. And then you've got all the coefficients, CIs, as I mentioned, and that determines the full polynomial. There's also an equivalent definition that a polynomial gamma is just a smooth curve whose k plus first derivatives equals 0, and k would be the order of the polynomial. And this class of curves would be parameterized by the initial conditions. So at time t equals 0, all the derivatives of gamma determine the curve. And they're related to the coefficients in the algebraic sense by this relation you just multiply by the factorial of the power. So the algebraic definition doesn't really lend us in a nice way to extending to Riemannian manifolds. For instance, what does it mean to add 2 points on a sphere? There's no good way to add 2 points on a sphere and remain on the sphere. So instead, we'll rule that one out and generalize this differential form of a polynomial. Because taking derivatives is more convenient in a Riemannian manifold. And so one quick note is that taking derivatives of vectors on a sphere, on a general surface of a Riemannian manifold is not in general well defined. You replace the time derivative with this covariant derivative. And just think of taking the real derivative in R3 if we're on the sphere and projecting that to be a vector tangent to the sphere. So it really does act just like the time derivative for an embedded manifold. So the first order polynomial is a very familiar object in differential geometry. It's called geodesic. You might have heard of these. They satisfy the geodesic equation, which is just the generalization of this to a Riemannian manifold. And it's determined by the initial position and velocity. And these have been well studied even in our field of computational anatomy, and Sarong and Tom are two of the main proponents of these geodesic methods. And we're just going to generalize this to k-order polynomials by repeatedly taking covariant derivatives of the velocity field. And so we get a higher order curve that's parameterized by a set of initial conditions. And these are all the time derivatives of the velocity as well as the position at t equals 0. And so the parameters of our model will actually just be these initial conditions. And given the initial conditions, you can integrate the differential equation forward and get the full curve at any future time. So given that polynomial equation, we have an algorithm for integrating this with fine time steps. In general, we won't have a closed form solution for a k-order polynomial on a manifold. Even the sphere, anything greater than k equals 1, does not have a closed form. So we'll integrate this, taking small steps and implementing parallel transport, which this is just a way to move tangent vectors. There's more. I'm going to give a reference on the next page that gives a little bit more detail. But suffice to say that this parallel transport and exponential map functions come with the manifold. They're defined by whatever Riemannian manifold you're on. And so if you know the manifold, you know what these, you can compute what these functions should look like. So on the right, you see in the sphere, I took a starting point and made up some initial conditions. The starting point, the velocity, acceleration, and third derivative jerk. And so when you integrate a third order polynomial with these initial conditions, we get the red curve. If we set the jerk equal to 0 at t equals 0, we can show that it stays 0 and it's equivalent to a second order polynomial. And you're seeing that quadratic curve in blue, and then the geodesic in black. So you see that these look really similar to the Euclidean counterparts, but it's important to note that we didn't just take a Euclidean polynomial curve and then wrap it onto the sphere somehow. We actually defined this intrinsically on the surface and then integrated it on the surface. Yeah?
So is it important how they loop around, or you just care about locally enough so once it gets outside the neighborhood, you're...
Generally, we're about just locally. But yeah, I mean, it's a good point that even the geodesic will return to itself eventually. And so, yeah, you'll always kind of have to have that interpretation. But yeah, for our purposes, just local. So now that we can integrate these things forward, and as I said, they're parameterized by initial conditions, how do we estimate the proper initial conditions given a set of data? This is one of the big contributions of this archive paper that I've posted online, where we derive an actual algorithm that extends the adjoint method of optimization to Riemannian manifolds. So we first linearize the system. We linearize this k plus 1 order ODE into a system of first order differential equations. We'll integrate that forward, and then once we get to our endpoint, we'll integrate these adjoint equations backwards. We have these adjoint variables lambda, which are like Lagrange multipliers enforcing our polynomial equation. Integrating these adjoint equations back to time t equals 0 allows us to interpret them as actual gradients with respect to initial conditions. And so in the Euclidean case, this actually just is the method of Lagrange multipliers with dynamic constraints and then applying calculus of variations. And we've extended that onto Riemannian manifolds. And the interesting things that pop out are the parts that are specific to the manifold. The log map here is just the inverse of at least locally, it's the inverse of the exponential map. And it's defined by the manifold. As well as the Riemannian curvature tensor, which for flat space, Euclidean space, and the Euclidean space is always 0. And so, to repeat, our algorithm will be to integrate the forward equation given our current estimate of initial conditions, initialize our Lagrange multipliers, our adjoint variables, to 0, integrate backwards in time back to t equals 0, and then take a gradient descent step. And this exponential map and parallel translation is kind of a natural way to take small steps on a manifold, and that's how we're going to update our initial conditions. So a couple of special cases are kind of important here. For k equals 0, that's the natural first case, we see that the polynomial equation is just gamma dot equals 0. And that means the same thing on a manifold as it does in Euclidean space. The gamma is constant, the curve is a single point. And if we estimate the curve, gamma, in such a way to minimize squared error, then we get what's called the Fréchet mean. And it's called a mean because in RD, this actually is equivalent to the arithmetic mean. So you would sum up all your data and just divide by n. But on a manifold, there's, like I said, no notion of addition. So you'd have to optimize your squared error in an iterative gradient descent. And this gradient descent for the Fréchet mean is what's implemented in atlas building procedures. So if you're familiar with the computational anatomy work that Tom and Sarang have done in the last 10 years or so, this is kind of the basis for a lot of that. So that's a way to find just a single mean. And this is actually just a special case of the polynomial regression method that I showed before. You just don't have to worry about adjoint equations and stuff. For the first order, we have geodesic regression. And this is pretty, this is now current work. Tom has submitted this and presented it at MFCA in September. And this is actually kind of a well-studied problem in differential geometry as well. The variation of geodesics with respect to initial conditions is governed by this equation here, which is a special case of our polynomial adjoint, and it's called a Jacobi equation. The resulting adjunct variables are Jacobi fields, and this is what Tom has in his paper using a much more conventional notion of Jacobi fields. And you notice we only have one curvature term instead of k-many. Okay, so until now you're probably thinking of the sphere or some other surface, but I want to move away and move into a shape space. Now, a Kendall shape space is the space of n many landmarks in d dimensions, but modulo the similarity transforms, transformation, or translation, rotation, and scaling. So if you look at the right, these two quadrilaterals are, they look very different. One is a scaled rotated version of the other one. But these would be represented by the exact same point in shape space. So shape space is unable to express translation, rotation, and scale. And the theory of this has been really well developed, and in particular for in planar shapes in 2D, this is nice and convenient. We have all the machinery we need to implement our algorithms. And the thing to take home about shape space is that by doing this, since the space can express this translation, rotation, and scaling, doing all of our statistics here and our regression here prevents us from being skewed by data which might be translated or randomly scaled or something like that. So the first data set we looked at was this classical Bookstein rat data set. The colivarium is the top part of your skull without the jaw. 8 points around the skull on a mid-sagittal section were demarcated for 18 subjects at 8 different ages, up to like 150 days. And we're interested in finding patterns in growth. So we fit geodesic, quadratic, and cubic polynomials to this data, and I'm showing the full data sets with all the fits here, with zoomed in boxes. You notice that the R squared goes up substantially between geodesic and quadratic, but doesn't change much when we go into cubic. And we see that in the figures, a geodesic regression here is almost like fitting straight lines. They're not exactly straight. Remember, this is in shape space, so it's not just a flat space. But it's not fitting the data very well. For instance, the data kind of bows out right here. And that's captured by the blue curve, the quadratic model. But moving to cubic, we see that the curve becomes much more wavy, and we're suspecting that this is actually overfitting the data. Currently, we don't have the tools to do anything more than a qualitative analysis of which model to use, which order of polynomial to use. But that's one of the things on our to-do list, is to come up with better statistical tests and such that will inform us when we're overfitting. And we also looked at corpus callosum data. So this is a set of segmented corpus callosums that we had 32 patients, and their ages were from 18 to 90. These are healthy patients, but they're from the OASIS Alzheimer's study. We took these segmentations and created corresponding landmarks data sets using ShapeWorks. And then we did the same thing. We fit geodesic, quadratic, and cubic. And here, the data is way too cluttered to show it all on one plot, so I'm just showing the trends that we estimated. Blue is age 18, and red is age 20. And so as you move to the foreground, you get them older and older. Our R squared kind of shows something interesting in this case, too. From k equals 1 to k equals 2, we don't see much difference in R squared, but when we move to cubic, we actually get a big jump in the R squared. And if you look at our curves, the quadratic and cubic curves, they look pretty similar. There's not a big difference there. And when we look down here, it's still somewhat similar, but we see that we're starting to overlap, and there's some interesting stuff going on. But what's really interesting about this data set is when we look at our estimated parameters. These are the initial conditions for the curve that we estimated for the cubic regression. So I'm showing here the initial velocity, acceleration, and jerk in blue, black, and red. And you'll notice that they're very nearly collinear. And this is important because, as we discussed in the archive paper, when the initial conditions are collinear, that implies that the curve, the path traced out by the polynomial, is the same as that of a geodesic, but with a different reparameterization of time. So that means that this curve could possibly be generated by a single geodesic regression, but where we reinterpret the time variable, we pass it through some cubic transform. So even though we have a 0.12 R squared for our geodesic regression. This is indicating that we might be able to get up to 0.21 by just reparameterizing the independent variables. And this is kind of a, yeah.
And that's not necessarily a good thing, though. To get better R squared, it might mean you're overfitting the data.
Yeah.
So that's part of the model selection problem that you mentioned.
Right. And so...
So, I mean, you're highlighting, I'm just saying, you're highlighting R squared 0.21 like that's the best one, but it may not be.
No.
It may be a bad thing, but it's not.
Right, yeah. Sorry, this is a little misleading. I didn't mean to say that it's absolutely the best. But within the class of geodesic paths and all reparameterizations, we would want to get the best match. And
not necessarily. You know, it could be, again, I mean, like if I go up to, like in polynomial regression, just in real data, if I go up to infinite order, I can get my R squared to go to 1 if I want. But I will just have this crazy curve that matches all the data perfectly that's overfitting.
yeah.
So I would disagree that even just in reparameterizations that you want to get the best R squared.
If you're free for to do any reparameterization, yeah.
Right.
I agree. And those should come in as...
So anyway, you have to solve the model selection problem to convince me that that's
okay,
that's
yeah, definitely. Yeah, that definitely is true. And any kind of statistics we come up for that are going to take into account the degrees of freedom in the model and stuff like that.
Known for groveling the noise you're anyway with R squared, that was so low.
Yeah, well.
So, yeah, sorry.
Go,
Sure, but yeah, I mean, who cares? It's insignificant.
So it's pretty low, but we suspect that that's mainly due to interpatient variability, and that if we actually did a permutation test or some kind of actual test, that we might actually still see significance. That there actually is a significant trend. It's just
yeah, my paper that he's citing there in the Cable one case, we found that even if that's low,
yeah,
it is significant in the permutation test. So it doesn't describe much variability, but it is a significant trend.
Yeah, but you're right. There's a lot of variability. It's kind of fuzzy estimates. So we're in the process of submitting this. We should hear back from CBPR within the next week or so, and I've put a preprint of an archive paper up online, and I hope to develop that into a real journal version by including mainly statistics that deal with the model selection problem. So what's missing right now are all the accompanying statistics. There's a whole host of statistics that go along with regression that statisticians use currently that a lot of them have hoped to be transferred and at least defined for the Riemannian regression case. And so I'd like to see which ones we can use and to sort of inform us on when we're overfitting. And I'd also, beyond descriptive statistics, I'd also like to develop some non-parametric tests to actually test for significance, to be able to reject or choose between two different models of curves. And finally, one thing that's underlying all of this is we currently lack a probabilistic model for doing this kind of regression. We don't currently have a solid generative model for the statistics that we would implement, and so we'll need to have this to reason about those statistics and prove stuff about bias and such. And Tom and I have been working the last year or so on some background work for that. Now, I've presented the two halves of the work so far, but now I want to just briefly mention that they're not so different after all, actually. If you think about if you're given a set of data and you just interpolate linearly between the two, this is really analogous to taking a set of 3D images and pairwise registering them so that we could generate a warped image anywhere at intermediate values. So we can really think of this binning plus registration as sort of an interpolation model, whereas our 4D reconstruction is more of a smoothing. So we model some smooth deformation and just fit the data in a least square sense, so that our motion estimate actually depends on all of the data at all the time points. Okay, so these two methods they fall under the non-parametric regression class of methods, but they are very related to our same problem of trying to find some trend in data. So we can really split this into non-parametric versus parametric regression. So that's where we stand. Looking forward, as I said, I'm going to be resubmitting our media journal paper in the next couple weeks. And then this summer, I hope to, planning to work with UCARE and do some real patient data MRI studies, and possibly working in a contrast change model to that, and submit another journal version with all that stuff around summer. Then in the fall, hope to have the statistical background worked out and be able to submit this regression work with accompanying statistics to a statistics journal, and then graduate in the spring, hopefully. So, thanks a lot. I'm sorry I ran over a little bit.
Okay, we'll open up the question to the open committee. I'll begin the open session first.
Okay.
You've mentioned Riemannian manifolds a lot. What does that have to do with deformations that you've been talking at the beginning?
Okay, yeah, great point. Oops.
No, I'm not in the job. I thought he was going to put that in.
No, I don't have a slide for it, but as I mentioned before, our model of motion ensures that our deformations are diffeomorphisms. And if you look at the actual space of all diffeomorphisms, this is an infinite dimensional Lie group, and it's actually a Riemannian manifold. So the class of Riemannian manifolds is actually really broad. It involves a lot of the spaces that we're accustomed to, and the diffeomorphism space is kind of a special case. It's an infinite dimensional version, but it's a special case of Riemannian manifold. So we could hope to extend these methods to diffeomorphisms. So that's the connection.
Okay, Nina?
Kind of a similar line maybe. If I have like a set of data points or subjects or something, how would I know if my space would be just like data Riemannian Euclidean space?
Like which space?
Versus Riemannian space.
Yeah. So right. So which space to model your data in?
Yeah.
Right. That's kind of the question. So a lot of times you'll know this based on like the form of the data. For instance, if you have orientation data that lies on the direction that something's pointing, that's obviously lies on the circle. Sphere data would be similar. But aside from that, you can also inform what model to choose based on what you want to consider, what you want to ignore. So we did Kendall shape space because we actually want to do our statistics without the influence of translation, scale, and rotation. But say we wanted to allow scale to influence our trends, and we want to find trends in scale. Then we could do size in shape space. There's Riemannian manifolds that are developed to handle that kind of setting. So it depends on where your data comes from and what parts of it you'd like to ignore, basically.
So in the first part, you're doing this reconstruction of the 40 images, and your work has much higher signal-to-noise ratio than everything else in the book, right? So how do you know that someone who's working with this data is not going to see it, and you haven't somehow made this overfit the data, and there's actually some error in the sensing that looks like it's perfectly fit, right? So someone assumes that there's not something there, but you've forced it into your model, and it looks like it's perfectly fit, as opposed to showing more noise.
So yeah, the basic question is that we're averaging all this data, and an average can sometimes not show all the variability in the data.
Right.
Yeah, so that's an important thing to consider, and I would really answer that with validation studies. The only real way to know that we're estimating motion properly is to throw in some really nasty data and see how it fails, because that's the only way that you get used to looking at these kind of things. But other than that, you've always got the option to bend and see if you ever snapped a shot of the liver in some really superior position, and that doesn't show up in your model, then you know that you've got something wrong. But yeah, I agree that's a kind of a challenge.
So is that leading towards some ad hoc kind of constraints you place on the solution?
So we do constrain the solution with our model, and in some sense you could say that they're somewhat ad hoc, but they're built to actually model a realistic deformation. So yeah, it's basically going from no model of the motion, or a model in which there's individual images and then geodesic regressions or whatever in between, to a model where it's smoothly varying at all times. So in terms of the actual motion estimate, I would say this model is no more ad hoc than bending an image and bending a non-similar image and bringing them into correspondence.
Yeah, but I was suggesting, what you were describing as identifying those anomalous behaviors that would tell you that you're not on the right track, that you're overfitting or making some other incorrect assumption, that those eventually become ad hoc constraints based on a particular application domain. Because you validate, you get an answer. What do you think?
Yeah.
You want to use this clinically because the docs need it desperately.
Right.
So what do you do? And so what it sounds like you do then is the application domain. You come up with some additional ad hoc constraints. It says the liver can't go higher than.
Yeah, and that's pretty likely. It'd be more of like a rejection criterion for a model, and just some sort of heuristics to tell when we know we've got a pretty unrealistic definition.
People who do the super resolution is also like they use the MAP framework and also a set of low resolution images to create a high resolution images, and it can also improve the SNR. So what's the connection between the 4D MAP reconstruction and the 4D, not 4D, just the MAP super resolution?
So yeah, that's a good question. The question is that there's algorithms which use a lot of previously acquired images. And then when you look at your image, you're going to use that as prior knowledge about what the anatomy looks like of a certain patient. And that will help you improve your image quality. And actually, that's one of a good point to bring up here, because we actually just place a flat improper prior on the image. We're not actually informing it in this setup as presented, but we could. This is open to placing whatever prior we would like to put on the image. And we've actually looked at some other non-empirical priors, like total variation, regularization, to try to get a nice flat image. But yeah, so it could be extended in here. When this map framework, though, kind of refers to a prior being on the velocity fields and the deformation instead. But the image is totally, yeah, it's open to that.
So can I say that the 4D reconstruction can improve the SNR just because you average the noise, and so the SNR is improved?
Yes.
And actually here you didn't do like the super resolution.
No. Yeah, we're not trying to use any previous images. And that's one reason that we might not want to use an empirical prior also, is that you have to remember that our application for that was radiation oncology, so these will be patients with tumors, and we don't want to use a prior of somebody without a tumor that would kind of tend to mask the actual tumor. So that's one big reason that we're not putting a prior on the image.
So you are using the gradient descent for your optimization. So how long does it take in your 4D reconstructions?
Yeah, that's a good question. So it depends on where the data comes from, but it's generally in the order of a day.
With respect to what problem size? Degrees of freedom?
Problem size, the amount of motion. If there's not a lot of motion, then you can get away with using less number of velocity fields, for instance, and you can optimize it a lot faster. It's anywhere between 6 hours to a full day. So,
okay.
But which would be enough. Generally, it's like 1 or 2 or a few days in between the simulation and the treatment.
Why don't you give an idea of what is the size? How many CT images, 512 by 512 CT images do you are involved in this?
Right. Yeah. And exactly. So the reason that this takes so long, this is actually implemented on a multi-core, and this is running on supercomputer. The data is just pretty massive. There's
It still takes a day.
Yeah, it still takes a while.
So it's not a day in the laptop, it's a day in a super.
No, it's not on my workstation.
Okay, that's
yeah, it's still pretty big, and
okay.
and I'm sure there's improvements that we could do, but we've actually tried some kind of naive ways to do a gradient or a conjugate gradient instead of gradient descent, stuff like that. We didn't see
But
really.
the gradient descent is is very slow, so have you ever considered more fancier methods?
Yeah,
Something that can become significantly faster.
Right. So we've tried to look at that somewhat. For instance, adaptive step size would be one kind of way to go, just right off the bat, to update our gradient descent. We're using just fixed step size gradient descent right now, which is, as you say, slow. We've looked into conjugate gradient. I did some tests with that. The problem is that conjugate gradient bounds your runtime by the dimensionality of the space, and the dimensionality of our variables, our regressive variables, are extremely huge. So we don't get a lot of we didn't get a lot of increase in the speed of convergence. But yeah, there's definitely a lot of opportunity for improvement.
So again, what is the size of?
So yeah, I was going to say. Yeah, so the images are each slice, for instance, would be about 512 by 512, and you might have 2,000 to 3,000 of these, and that's the input data, and then your output would be the same XY dimension and about 80 to 150 slices in the Z direction. So it's a pretty big problem. What's up?
What's this size then, like
in gigabytes? So a couple of gigabytes of raw data, and once we model it, our independent variables are up to like 10. So because we have many velocity fields, if we do it really finely,
is it up to 10 independent variables or up to
10 gigs? Yeah, depending on how we want to do it. Because we can discretize time. We have the freedom to do whatever discretization. If we want to do a really fine one, yeah, we can basically. There's no sky's the limit.
So assuming you solve the model selection problem, you're starting to talk about something I think is pretty interesting in this time condition. Can you talk a little bit more about what you might learn?
Yeah. What I thought was interesting about that is that maybe I can just go back real quick. Currently. People know that they're doing regressions and they have an independent variable that might be even not have a natural scale, for instance, a clinical variable that is just some number, and they might want to have some monotonic transform of it that would give them a better regression, and they could actually rescale that in clinical practice to improve its kind of predictive power about certain outcomes. Currently, people kind of do some sort of ad hoc things, like they would, for an aging study or a growth study, they might normalize, instead of by age, they might parameterize the regression by skull volume. And so people are kind of like searching for the best parameterization to use to find the most reliable trend. And vice versa, once you find a very reliable, a very solid trend, then that independent variable becomes really useful for predicting your responses. So I thought it was interesting that without even trying to estimate a reparameterization, it kind of just fell out. And we don't have to modify this to independently estimate a pre-parameterization or a shape variability. It just does it automatically. So. Anybody else?
Right, thanks, Jacob.